So in this class we will continue what we have learned in the first session. We were talking about semiconductors. So let us understand this small concept. Suppose there is an atom. There is a atom. What does the atom has? Atom has a nucleus and electrons are rotating around the nucleus. So in the first orbit you can have 2 electrons. In the second orbit we discussed you can have 8 electrons. So there are some specific numbers. So this is a stable system. So here if you take this atom, how many electrons are there and how many protons are there? So number of electrons is 2 plus 8. 2 plus 8, it is 10. And how many protons are there? Protons are also 10. So what is the net charge? What is the net charge? See, electron charge and proton charge is same, but electron has a negative charge and proton has a positive charge. Electron mass is less when compared with proton, but their electric charges are same. So here you have 10e, which is proton charge, minus 10e, which is electron charge, which is equal to 0. Okay. Suppose this net charge is not equal to 0, then you call it as a ion. You have a situation where you have 10 protons and 9 electrons. So is the net charge 0 here? It is not 0. So it is in a ionic state. So here there is a net electric charge is there. That net electric charge can be a positive value or can be a negative value, depending upon the number of electrons present or the number of protons present. More protons means more positive charge. More electrons means more negative charge. So when you take this atom, the electrons in the outer shell are called as valence electrons. We talked about this. Okay. So you have a configuration like this. Let us say for some other atom, the configuration is like this. Okay. So 2 here, 8 here, and only 1 in the third orbit. Basically we have to supply energy to this electron and we have to move the electron. Why we are interested in moving the electron? Because electron moves, creates electricity, creates current, isn't it? We have to create current, we have to create electricity, we have to create conduction. We are doing the whole thing because we want to conduct electrons. So in the outermost shell, the electrons that are available are called as valence electrons. When you give energy, they convert into, let us say this electron, it left this atom and it came out. This is called free electron. So I hope you understood the difference between valence electron. Valence is with the atom, free means outside the atom. So in the previous class, we'll discuss one more concept now. In the previous class, I was telling you why some behave like conductors, why some behave like insulators, why some behave like semiconductors. We came across a concept called forbidden energy gap. Forbidden energy gap. Now this was our valence band and this was our conduction band. So the electrons which are in the valence band, you provide energy, they move to the conduction band. So here they are in free state. Here they are attached to the atom. Okay. Now what happens? Suppose you have This is the system here. This is the nucleus, and there is, let us say, there is an electron. So this electron is moved from this place and it comes out. It becomes a free electron, let us say. So what will happen to this spot? Will any proton come over there and occupy that? No. The protons, neutrons are in the nucleus only. So that place is basically vacant. It is basically vacant. So we call this as a hole. Technical term is hole. So hole doesn't mean that you punch a hole there. It is not physical hole. It means lack of electron. It means lack of electron. Okay. Earlier there was a electron was there. You provided energy. It moved to some other place. This place you have to assume that it is now vacant. The technical term is hole. So that means this place is now lack of electrons. Okay. It is like your musical chairs, or let us say some chairs are kept in order like this. Okay. There are 4 chairs and 3 people are sitting over here. Okay. 3 people are, it's like a queue. Suppose this fellow came over here. What will happen? This fellow went here. There is a vacancy here now. This fellow will occupy the vacancy. Then when this fellow moves, this fellow will occupy the vacancy. What is basically happening? You call this person as an electron. The electron is moving, no? So that is the conduction of electricity. Okay, this is the concept involved. Okay, so basically the whole business is to move the electrons. So we have seen that when this forbidden energy gap is very high, you are calling that as insulators. When it is less, they are calling it as semiconductors. Okay, and in conductors there is an overlap. So for semiconductors, some energy has to be provided. That means you have to heat them. When you heat them, what will happen? The electrons from the valence band, they will move to the conduction band, and therefore there is a conduction happening. Okay, so this is the property of semiconductors. So we have a situation like this, that this is our conduction band. This is our valence band, and this is the gap, E gap. So originally the electrons were here. So from here to here they are moving. So now the electron is here now, let us say. Okay. So here there is a vacancy. Similarly here there is a vacancy. There is a vacancy here. If they are moving to the conduction band. Okay. So when we talk about charge carriers in semiconductors, when we talk about charge carriers, you say one charge carrier is the electron itself, the free electrons. Which type of electrons? The free electrons are the charge carriers, not the valence electrons. And another type of charge carrier is, this you call it as negative. Another type of charge carrier is holes. This you can call it as positive. Hole doesn't mean a physical hole. Hole only means vacancy created by movement of electron. Okay. So because you are calling this as negative, you are calling this as positive. Hole only means vacancy. Please clearly understand this term. Okay. Do not think that in the hole some proton will come because positive charge is there, proton is there. No, it is not like that. When the hole is filled up with electron, basically it is like this. Like I have shown that system of chairs. Imagine that musical chair. Musical chair, what happens? People keep running around. Those running around is like electrons. They're creating vacant seats. They are like holes. Okay, the holes have to be occupied by the electrons only, not by the protons. So this is one thing. Now we will look into one more concept. See, let us take the case of carbon. Okay, So carbon 6, so its atomic structure is something like this: 2 here and let us say 4 here. So ideally it should have 2 8, but it has 2 4, so it is 4 short. So suppose 4 electrons are added over here. How many electrons and protons here now? You have 2 plus 4, you have got 6 electrons and 6 protons. Is it stable now? It is stable now. So suppose these 4 electrons are knocked out by providing some energy. How many electrons will be left? Then how will be the diagram? Suppose these 4 electrons are knocked out, because these 4 electrons are valence electrons. Then also what will happen? When they are knocked out, only 2 electrons will be left. It is stable. So is it actually stable? So suppose I give energy and all these 4 electrons have been knocked out. Then the diagram will be something like this. It has got only 2 electrons. These 4 electrons, valence electrons, from VE, valence electrons, they have converted to FE. But what will happen to the charge, you see? Now how many electrons are there? There are 2 electrons, but protons remain same only. 6 protons. Is it desirable? It is basically unstable. Is it stable or unstable? Means it is unstable. You can add also 4 electrons. Let us say I add 4 electrons here. Okay, atomic structure becomes more stable now. 2 is there, 8 is there. Alright. But in this situation, the third situation, what will happen? How many electrons are there now? 8 electrons on the outer side, 2 electrons inside. Now it has got 10 electrons. But how many protons? 6 protons. Is it stable? It is unstable. Okay, it is unstable. This is also unstable. This is also unstable. Originally it was like this. Okay, so in order to keep it stable, what can be done? So you have added here 4 electrons like this now. Suppose you had a concept that it shares these electrons with the neighboring atoms. If it is possible, then what will be the situation? You still have 6 electrons and 6 protons. The system remains more stable. We will see how it is. Remember we were talking about interaction energies. We were talking about interaction energies, right? Suppose we have a system like this where you have this nucleus and you have this electron over here. Alright, and I bring another atom here. Okay, it is this nucleus and it is the electron here. Okay, and the electrons are not moving, but they are sharing. That the final diagram will be something like this. This is nucleus, this is nucleus. Alright, and here it is like this. Okay, they are mutually sharing the electrons. So this sharing of electrons is called formation of covalent bonds. Why? Suppose you take the case of carbon. Carbon, what was the situation? See, carbon, the situation was like this. This was the nucleus. This was the situation. 2 here and 4 here, let us say. Alright, I put another atom here, 1 atom here, 1 atom here, and 1 atom here. Alright, so here also 1 electron will be there. Here also 1 electron will be there. Here also 1 electron will be there. And here also 1 electron will be there. So this is our atom 1. This is 2. This is 3. This is 4. This is 5. Atom 5. Okay. So what is happening here? See, basically in the outer shell you should have 8 electrons. 4 were already there. But you bring them very, very close. They will form a bond by sharing of electrons. So that type of bond is called covalent bond. So in that situation also what happens? You are getting 8 electrons in the outer shell. So the system is stable. But originally the atom was how many electrons? it will have only 6 electrons only. 2 in the first orbit, 4 in the second orbit. Total 6 electrons will only be there. They are only just sharing their energies. They are just sharing them. So this type of bond is called covalent bond. Okay. So basically covalent bond means it is sharing of electrons to form a more stable structure. Okay. So for that, for any covalent bond to happen, you should have at least one pair of electrons. You should have at least one pair of electrons. Otherwise, you cannot form a covalent bond. But is it that you should have only one pair of electrons? You can have two pair of electrons. You can have three pair of electrons. You can have multi pair of electrons. If it is one pair of electrons, it is single covalent bond. If it is two pair, it is called double covalent bond. If it is three pair, it is triple covalent bond. Okay. So we can see some examples here. You can see the example of let us say, because this point is very important. While talking about semiconductors, you need to understand what is this covalent bond. Suppose you take the case of oxygen. You take the case of oxygen. What is the atomic number? Atomic it is 26, right? It is 8 now. 26. Okay. So how the atomic structure will look like? It will look like this: 2 here and 6 here. So 1, 2, 3, 4 and some 5, 6 like this. Okay. So basically oxygen, what it does is it forms a double covalent bond. Okay. So these two electrons can be like very, very close, and it forms like this. Okay. It forms covalent bond like this. Okay. So these two belong to this this is our atom 1 and this is our atom 2. So in the outermost, how many you should have? You should have 6. So 2 here, 2 here and 2 here. Even for this also, 2 here, 2 here and 2 more here. I am talking only about the outermost. So how do you show this? Means you can show this as with a double line. Oxygen, this is oxygen, oxygen with a double line. Okay. Take the case of nitrogen. Nitrogen, it is 7. So the combination is 2, 5, right? So if you if I draw only the outermost shell, the first orbit will have 2, the next orbit will have 5. So it will have 1, 2, 3, 4 and 5. In nitrogen, what happens is it forms a triple covalent bond. So the diagram will be something like this. I am drawing this is my nucleus. Okay, 1, 2, 3 like this. Okay, so here also you will have another 1, 2. This is the nucleus. So this is one nitrogen atom, this is another nitrogen atom. So how many are shared here? 3. How many are shared here? 2. In the case of carbon is a special case that we will see. So here 3 are shared. You can write N, 3 dashes and N. So it is a triple covalent bond. So this covalent bond formation is happening to make a more stabler structure. Okay, here it is a double covalent bond. So in the case of carbon can form, see, when you talked about carbon, so carbon was 6, carbon atomic number is 6. So you have 2 here, and in the outer shell you have got 4. Okay, so here it can share, here it can share, here it can share, here it can share. So it can form single, it can form double, it can form triple and quadruple also it can form. With different atoms it will form different covalent bonds. Okay, so this is the concept behind the covalent bonds. We will see this where how this is used in the formation of a semiconductor. So when we talk about semiconductors, we have basically two types of semiconductors. One is intrinsic semiconductor and one is extrinsic semiconductor. Okay, intrinsic means no impurities, no doping. Okay, here we dope. Dope means you bring some external impurity. Here you don't do that. It is natural formation. It is like this, you take milk, you add water to it. What is that? Adding water to milk. Milk is natural. If you are adding some water to the milk, it is doping. So in the case of intrinsic, it is like a pure semiconductor. It is impure semiconductor. In simple language, you can understand like that. So intrinsic semiconductor, how they look like, let us understand that. So let us draw the structure. See, silicon, we have discussed. What was the atomic number? 14. Combination 2, 8, 2 plus 8, 10, 4. So the outermost orbit will have 4. Okay. So suppose silicon is there. I will put like this. Okay. So here, can it form covalent bonds? It can form covalent bonds with the nearby atoms. Okay. That's how, that's how they behave like, similar to the case of carbon, it forms covalent bond. So this will look something like this. If I draw a sample, I take a sample will not have single atom. It will have multiple atoms, isn't it? It will have multiple atoms. We are just drawing the exaggerated diagram. I will put another silicon here. So it is forming a covalent bond. You put it here, you put it here, you put it here. You put another silicon atom here. So one here, one here, one here, and one here. Okay. Below this, you put another silicon. It is one here, one here, one here, and one here. Put silicon here, one here, one here. It is forming covalent bond here, and like this, and so on and so forth. One here, one here, one here, and one here. So this is how the arrangement is like. Okay, you can take a big lot. We have taken a sample where how many atoms are there? 1, 2, 3, 4, 5, 6, and so on and so forth. See, all these electrons, they are the valence electrons. Okay, and these are all neighboring electrons, neighboring atoms. So this silicon atom is forming a covalent bond with this silicon atom. Okay, so this is the system now. Is it stable now? It is stable now. So what you do is, so this, in this whole system, are you finding any impurity? Are you finding any external parameters? Did I add anything to this? So it is totally pure. It is an intrinsic type of semiconductor. Why this system will behave like a semiconductor, that we will see now. Suppose I target this particular electron. Okay, what I do? I give some energy. I give some energy to, let us say, this particular electron. What will happen? Right now this is in the valence band. Now it will move to the conduction band. So when it moves to the conduction band, it will move from here, isn't it? So what will happen? Here temporarily a hole will be created. Students, hole doesn't mean the physical hole. A vacancy is created. Okay, what can happen? Some other electron can fill this vacancy. Okay, then a vacancy is created here. Some other electron can fill this vacancy. Okay, you can pick up from somewhere. So you can say, so you can draw over here. Okay, one more silicon. It is like this. So this fellow become vacant. This fellow may occupy, right? What is happening? The electron is moving. So it is conducting. So when did it conduct? I provided energy. What is this energy? It is in the form of heat energy. So this intrinsic semiconductor, you understood how it works. So when you provided some heat energy, see at normal room temperature they won't behave like conductors. When you provided heat energy, one particular electron moved, okay, then somebody else replaced it, then somebody else replaced it. If you provide more energy, the conduction will increase. So what is happening? You are increasing heat, the conduction is going up. Now recollect what you have studied in electrostatic current electricity. There in conductors, when you give more heat, the conductivity actually drops. This is the case of pure conductors, which you have studied in current electricity chapters and all that. Remember those curves, resistivity, conductivity, we have discussed these points. But this is a special case. This is the case of semiconductors. This is the case of semiconductors. Here you are giving more heat. More heat, what will happen? More valence electrons will become free electrons. Then more holes will be filled up. Then conductivity is going up actually. So here more heat, conduction is increasing. But there more heat, conductivity is dropping. So this is the behavior difference between a conductor and a semiconductor. A conductor and a semiconductor. It's a very important point. Okay. So this is the case of intrinsic semiconductors. So there is no doping here. You haven't added any impurity to this sample. Okay. So this type of semiconductor is called intrinsic semiconductor. So some other concepts we'll see in the next maybe session. So make a note of all these points.